So we're going to put everything together now, our imaginary roots along with our real roots, and see what kind of lovely pictures we get. So on the side here, we have this polynomial, x to the fourth minus 3x squared minus 4. And we should be able to totally analyze it. As always, I stress getting a picture of it, whether you're going to do it on your graphing calculator or on your Desmos app. So here we have a lovely picture of it. What do we realize about it? One, we realize that it is to the fourth power, so that we know we have two tails that are pointing either up or down. And since it's a positive x to the fourth, the tails are pointing both up. What we see here, we have two obvious zeros. So we have two real roots. Those are the numbers 2 and -2. But if it's to the fourth power, then we must have two imaginary roots. But the problem is, what are they? We can't see imaginary roots on this graph. So we have to learn, how can we find those imaginary roots? Well, we kind of work backwards. We know we have the 4 roots. So we know if we have 2, it came from x minus 2. And if we have -2 as a root, it came from x plus 2. So then what do we have here? Well, we have to revisit our factoring. That's right. So we know x minus 2 times x plus 2 is x squared minus 4 times something gets me x to the fourth minus 3x squared minus 4. Well, we could do multiplication. We could try and figure it out. We could say, all right, x squared times what is going to get me x to the fourth? Well, that must be another x squared. -4 times what gets me -4? That must be a plus 1. All right, if I check my bridge is x squared, my tunnel is -4x squared, and if I add my bridge and my tunnel together, I do get -3x squared. All right, so now I've figured out, if I clean this up over here, I figured out that my other polynomial that I multiplied by must have been x squared plus 1. So now I can solve that to find my other two imaginary roots. I just say x squared plus 1 equals 0, x squared equals -1, x equals plus or minus the square root of -1, which we now know is I. So my other two roots are a positive I and a negative I. There, I have 4 roots. Now, if it didn't factor that well, we could have always just done long division. We could have always said x squared minus 4 goes into x to the fourth minus 3x squared minus 4. We could have divided it out and figured out what my other factor was. Now, just to introduce a couple of new terms, these are called linear factors, because linear means line, and line has a degree of 1. This is not a linear factor. It is still a factor, But notice because it's squared, it's not a linear factor. All right. How about if we go backwards? How about if I give you the roots and you have to come up with the equation? Well, that's not that hard to do, considering that's exactly what I did over here. All right, so we recognize that there are 4 roots. 1, 2, 3, 4. And I'm going to tell you something about these imaginary roots in a minute. But let's not get ahead of ourselves. I always like to just set up a little table. All right, I know I have 4 roots. So my possible answers are, oh, not my possible answers. I know my answers are -2, 3, minus 4i, and positive 4i. All right, well, -2 must have come from x plus 2. 3 must have come from x minus 3. And this must have come from x plus 4i. And this must have come from x minus 4i. Now, it said find the equation of this polynomial. Well, that means we have to rewrite this. Well, this number should have always been set equal to 0, so we should have put that 0 there. Likewise, we should have had a 0 right there. So anyway, getting back to this, we have to write an equation. And you've never seen an equation written with i's in it. In other words, you can't give me this as an answer. The 4 linear factors set equal to p of x and say, well, that's an equation. No, can't do that. Because what we have to do is we have to take care of those imaginary numbers and turn them into real numbers. In other words, we're going to have to take a step here, and we're going to have to actually multiply these factors out. Well, that's not hard to do because this is why we tortured you with factoring. You should realize that these are a difference of squares. We know that x times x is going to get me x squared, and we know that the bridge of negative 4ix and the tunnel of positive 4ix are going to cancel each other out. So I'll just be left with minus 16i squared. I squared is -1, so this must be x squared plus 16. Okay, now, finally, over here, I can write my grand answer, the equation given these roots. I don't have to multiply them out now. I can say it's x plus 2 times x minus 3 times x squared plus 16 gives me this polynomial. Now I'm going to go back to this little box that I said I was going to come back to later on. These are imaginary roots, and imaginary roots always are in pairs. And not just imaginary roots, they can be complex roots. Imaginary roots, complex roots are always in pairs. In other words, you can't just have -4i as an answer. It always has to have its brother or sister, whatever you want to call it, of its positive. So you can't just have the root 3 minus 2i. It must have its sister root, 3 plus 2i. They always have to come in pairs, because after all, they're the square root of a negative number. And we have the principal root and the negative root of that square number. So the toughest one we're going to have is this one right here. We're given roots that are a little nasty looking. Why are they nasty looking? Well, because we got some square roots in here, and we've got n imaginary number? Huh. Well, again, I'm going to set up my chart. And I'm going to give myself a space for every answer that I have. So I've got negative square root of 2. I've got positive square root of 2. I've got 3. I've got 1 plus 2i. But guess what? This is actually a question from Engage New York. So you have to have that higher level of thinking. You have to say, wait, Mrs. Trulin just took the time over here to talk about this brother and sister imaginary complex roots are always in pairs. So, even though they said this is a root and they didn't list it, this is also a root. They have to come in pairs. So they tried to trick you on this one. So this is actually a degree of 5. So going backwards now, this must come from x plus radical 2. This must come from x minus radical 2. This must come from x minus 3. And now this comes from x minus 1 plus 2i. And this one comes from x minus 1 minus 2i. All right, so now how am I going to get an equation from all this? Well, this is where you have to be very strong at multiplying these out. So we'll take these right here. This, whoops, it's all as 1. Let me see. We'll take this x plus radical 2 and this x minus radical 2, and I'm going to multiply those out. Why? Because we usually don't see radicals in equations, although we could leave this because it is a linear factor. I just like to say it prettily as x squared. These are going to cancel out. Radical 2, that's going to be minus 2. Oh, this x minus 3, thank you. Don't need to multiply that. But right here, x, well, let me do this. Minus 1 minus 2i, x minus 1 plus 2i. If I multiply that out, I have a trinomial times a trinomial. All right, here we go. There is a shorter way to do this, but I'm not going to show you. See if you can figure it out. X times x is x squared. So this is what I'm doing, distributing the x. All right. Now I've got to distribute the negative 1. And finally, I've got to distribute the negative 2i. See if you can see that shorter way. There is a shorter way, but I'm not going to tell you. All right, minus 2ix plus 2i minus 4i squared. All right, so let's clean some things up here, and we're going to have our last factor. X squared. Are there any other x squareds? Nope, that can come down as x squared. Minus x and another minus x is minus 2x, and that's it for x's. So a positive 2xi and a negative 2xi, see these are the same because I can multiply in any order, cancel each other out. A minus 2i and a positive 2i cancel each other out. I have a plus 1, and remember right here, this is really going to be a plus 4 because negative 1 times negative 4 is plus 4, so that results in a plus 5. Now, doesn't it make sense that these complex roots, when multiplied together, get you a trinomial? Because complex roots come from the fact that you couldn't factor a trinomial, and you had to do the quadratic formula, or you had to do completing the square. So finally, we get the equation who has the roots of negative radical 2, positive radical 2, 3, 1 plus 2i, and 1 minus 2i. Anybody see the shortcut yet? Anybody? Bueller? Okay, see you tomorrow.